In this part, we're going to look at machine learning for the next few lectures. We're going to start in this lecture with a basic introduction to machine learning and also start focusing on supervised learning. I'm going to talk a bit about the difference between regression and classification, but we're going to start by looking at regression problems, which are easy to visualize, and so see some techniques and some aspects of this approach. So basically, for this first lecture, we're going to look at the idea of machine learning and what it is useful for, and then look specifically at supervised learning, focusing on regression. Now, for this part of the semester, we are going to take a different approach than what we've been doing previously. Machine learning is very important in bioinformatics, and the importance of machine learning in bioinformatics is growing as more and more techniques come that can solve important problems in bioinformatics. But it's not a set of algorithms that are specific to bioinformatics. So it's a more generic approach, and we will not look into them in as much depth as we did previously for algorithms that are very specific to bioinformatics, such as sequence alignment, phylogenetic trees, and so on. So our approach here will be a bit broader to give you a more general idea of different machine learning approaches, and more focused on concepts and techniques, and rather than in the details of these different algorithms that we're going to cover. So the idea of machine learning is not extremely recent. We have even about 60 years ago already this notion of trying to give the computers the ability to learn to solve problems without us having to specify how the problems are solved, so without having to be explicitly programmed. And the idea, using this more operational definition by Mitchell, is that we have some task that we want the computer to perform, we have some measure of the performance at that task, and we also have data, experience, or some examples that can illustrate how the task will be performed. And we say that the computer program is learning from this data if, as we present more and more data, the performance can improve according to this measure when the computer is performing this task. So this is the idea of machine learning. If we can make the performance at some task improve by giving data, then we have a learning program that can learn from experience. And these would be basically the three things that we need to define in order to completely specify a machine learning problem. What is the task we must perform? How can we measure its performance? And what is the data we are using to improve the performance of the learner? A generalized example that is easy to understand is, suppose that you want to create an automated ticketing desk where people could telephone and ask for information about flights and book flights and buy tickets and so on. So this would be the task would be to take a voice input from a phone call and identify which segments correspond to each element of what the customer is saying. For example, please book me on would be a request for booking a flight. Flight 21 would be the identification of the flight. Philadelphia, Dallas would be cities, and from to will indicate the origin point and destination, and so on. So this would be the task that we would like our automated system to do, to identify automatically these elements during a conversation, so that we could then extract what the customer wants. The performance measure we can have would be by looking at our annotated voice records. This is the data that we are using. Would be to check if our learner is correctly identifying the expressions. And the data that we would use would be a large data set of voice recordings, with the annotation saying, for example, from second 2 to second 5.3, the person was asking to book a flight, and so on. And this way we could check if the system was learning. So there are different types of problems in machine learning. We could try to predict something continuous like prices or quantitative measures of gene expression or something like that. This would be a regression problem. We could have classification problems where we want to determine if an example belongs to some class. This is very used in bioinformatics, for example, in gene prediction, where we have different classes of 4 segments of DNA sequences, which can be functional genes or not functional genes. So we could have to separate them in these classes. We can have also different problems like associating entities, examples, or grouping those that are similar. Clustering is very used in data processing in general, and so forth. So in bioinformatics, there are some fields where machine learning has become very important. In sequence processing, even in supervised learning, for example, for predicting genes, or unsupervised learning for grouping sequences, machine learning has become very important. Recently, for protein structure prediction with deep neural networks, there has been a huge advance in the ability to predict protein structures from sequence, and also studying the patterns of gene expression in tumor cells and normal cells for cancer studies and so on. There are many examples here in bioinformatics. And machine learning is especially good for solving problems for which we cannot think of a specific algorithm or explicit rules for solving them. One example where this is easy to understand is the identification of handwritten digits. This is a classical machine learning problem because identifying handwritten digits is very important for postal delivery. People write the postcodes by hand, and then the post needs to be sorted to different regions. And so automating this part where some machine can read the handwritten postcodes and forward the mail appropriately was very important. So there was a lot of research into this area. And one difficulty here is that we cannot think of a explicit algorithm by which we could check if some pixel is black or white or something like that, and decide that this is a 9 and this is a 6 and so on. So we can see that easily by looking at the handwritten digits, but we cannot think of an algorithm we could implement that could solve this problem. So for this, what we do is we use machine learning. We use something, for example, like a neural network that will adjust different parameters based on the labeled data that we have. For example, we know that this should be 96203, so this is the correct answer in this case, identifying each digit like this for this case and so on. So we have a large set of labeled examples. And now the machine learning algorithm will adjust the parameters of our model. For example, in a deep neural network, it could be hundreds of millions of parameters, and create an algorithm that can solve our problem. Of course, this will be a very confusing algorithm for us to try to understand, because if it's a neural network, then it will be millions of operations like multiplication, sum, and so on. But it would work. You would give an image of handwritten digits. It would do all of those operations on the input, and after millions of sums and multiplications, which the computer can do very quickly, it would output a number between 0 and 9 and tell you which was the digit that was written there, and actually get it right most of the time. So basically, what we can see machine learning as a way of producing these algorithms that solve problems when we cannot think about how the algorithm will be, how to write it, but we can obtain it by adjusting the parameters of a very large model, or sometimes it can be a smaller model, but adjusting these parameters so that we have our final algorithm. This is good when we have large volumes of data, And in bioinformatics, we have things like sequence databases or the protein data bank that have huge amounts of data. And when we have lots of data, then it's easier to use machine learning because we have many examples to help us fit our models. And it's especially good when we do not have the recipe to solve the problem. So if we have the right data, we can, instead of figuring out what the algorithm is, just give the data to the machine learning algorithm, and it will generate, it will instantiate a specific algorithm to solve our problem. Okay, so let's look at some basic concepts in machine learning. We will call the set of possible hypotheses from which we are selecting one specific solution the hypothesis class. And this is something we need to assume about the solution, because when we fix the hypothesis class, we are saying that our solution to our problem will be one of these hypotheses. For example, suppose that we have two types of things. Let's call them red and blue. This is just an abstract problem. We measure them, a sample of the red things and sample of the blue things, and we have these two features, these attributes, which are these coordinates here. Let's call them x and y for now, and we want to separate red and blue. So we want to find an algorithm that, given the coordinates of a point, it will tell us, well, whether it's red or blue, and we need to find that algorithm based on the data that we gathered so far. So one thing is, we could start with the hypothesis class as being the set of horizontal lines. We could create a model to represent this hypothesis class, and this would be, for example, our model, which tells us that a point is blue if y is below this parameter θ1 here. So by changing the value of θ1, we could be considering lines that are higher or lower as we increase or decrease the value of θ1. And now we can use this to obtain a specific hypothesis. For example, if we set θ1 to 0, our algorithm would be to check, to predict if something is blue, we will take the second coordinate here, compare it with 0, and if it's below 0 or equal to 0, it's blue, otherwise it's red. So by adjusting this parameter here, we can obtain a specific algorithm to distinguish between red and blue. We could do it with a different hypothesis class, for example, using circles of radius 1. In this case, we would have two parameters, which will be the center of the circle. And once we instantiate these parameters, for example, -1 for θ1 and -1 for θ2, this would give us this circle, and this would give us an algorithm to predict if something is a blue point. If it falls inside this circle, then it's blue, otherwise it's not. So this is the basic concepts. The hypothesis class is the set of all hypotheses. For example, the set of all circles of radius 1, or the set of all lines in these different hypothesis classes. The model is a mathematical representation of this hypothesis class, usually with parameters that we can adjust to obtain each particular hypothesis. So in this case, the hypothesis class will be the set of circles of radius 1, and the model will be this particular mathematical expression that we can that has these parameters we can instantiate to obtain each hypothesis. And then we obtain our hypotheses, which are instances of the set of parameters in the model. For example, one hypothesis would be to use one line, a horizontal line passing at 0, so that if the second coordinate of a point is less than or equal to 0, we would classify that as blue, red otherwise. So this hypothesis gives us one algorithm to classify points, or another, using the other hypothesis class, we would get this particular hypothesis by instantiating θ1 and θ2 to -1 in the circles hypothesis class. This would give us the algorithm then to predict if something is blue. So we would compute this expression, the x coordinate plus 1 squared plus the y plus 1 squared, and if this is below or equal to 1, we would classify it as blue, otherwise red. So the hypotheses give us the algorithms for solving our problem, and we obtain them by instantiating the parameters of the model, which represents the whole class of hypotheses. Now, when we specify a class of hypotheses, in this case the line or the circle, we are introducing what is called inductive bias. So we are biasing everything because we can only find hypotheses inside the hypothesis class. If our hypothesis class is the set of horizontal lines, for example, we will never find a vertical line there. It does not exist in the hypothesis class. But we must do this, we must restrict the set of hypotheses we are considering in order to be able to generalize from the data that we have to anything that we will find in the future. And this is easy to see when we consider the assumptions that we need to make in order to plan future events. For example, try to plan your day for tomorrow without assuming anything about gravity, oxygen, whether or not the universe will exist, something like that. This makes it impossible because we cannot take into account all the logical possibilities. We need to restrict them in order to be able to make any decision or extrapolation from previous events to future events. So whenever we need to extrapolate something or generalize, we need to restrict the hypothesis that we are considering, and this is the inductive bias, the selection of an hypothesis class that does not cover all possibilities. Okay, so let's look at some machine learning types of problems. One that we're going to look at in future lectures is unsupervised learning, and the idea here is basically to try to find some structure in the data. We have the feature values, which is what we can observe in the examples, in the data, now and eventually in the future, but we are going to present those to the learner in order to obtain new feature values, new features that help us understand the data better. One easy to understand example of this is clustering, where we want to group together things that are similar and in different groups things that are more different. So in this example from this paper is clustering applied to images using features from the images, which are color distributions and so on, but also features from the pages where the images are found on the internet, such as labels and text associated with the image. So one example that we have here, this top cluster, we can clearly see that the images are very similar, but then we have another one here where we have images with similar color distributions, but we also have a planet here, probably Pluto, and then we have Pluto, the Disney character, here on this image. So these were also grouped based on the labels found in HTML. But the idea is that we don't have a previous notion about whether the images should or should not be in some particular class, but we are presenting everything to the learner, and the learner will sort the examples out and tells us new features, which are the groups where each example will belong to in this particular case. So in unsupervised learning, we do not have labeled data. We want to find structure in the data, and this can help us organize things better, understand the data, and can be even a first step on other learning problems, but it can be useful in itself. For example, in bioinformatics, clustering is very used in many different applications, and in particular, hidden Markov models are very used in bioinformatics for processing sequences, for comparing sequences, grouping sequences together, and so on. So this is one example of an unsupervised machine learning approach that is very important in bioinformatics. And we're going to dedicate a lecture to that in a few weeks. Another kind of machine learning problem is supervised learning. In this case, our data contains not only the features, which are those values that we can measure both in the present data and in future examples, but also the target values, which are those values that we want to predict from the features. So in supervised learning, we have a set of data, the training data, that contains all of these values, both the features and the targets, and we can then feed the features to the learner, check what the learner is outputting, what it's predicting, and measure the error by comparing the predictions of the learner with the corresponding target values that we already know in the training data. So this is supervised learning because we can use this comparison between the output of the learner and the target values to supervise the performance of the learner and to guide it in order to be able to output values that are more approximately correct. So if the target values are continuous, we need the learner to approximate them as well as possible, and this is a regression problem. If they are discrete classes, then we need the learner to separate the different examples into different categories, into different classes, and so this is the classification problem that we're trying to solve. So one example here that is easy to understand is face identification. We can give our learner a large number of examples of faces and non-faces, for instance, and then the learner can be applied, the final hypothesis that we obtain after learning can be applied to processing images and identifying where faces occur. Of course, this can lead to some errors, false positives, like happens here, where this pattern on the wall was assumed to be a face 2, or in some cases false negatives. For example, this woman has the face line slightly slanted, so it's not vertical, and this result, the hypothesis that we found here, was not able to identify the face in that case. So another kind of machine learning problem is reinforcement learning, where we want to optimize the performance of the learner, but we do not have feedback on every decision the agent is doing. So we can, for example, if we are training a system to drive a car, we know that if the car crashes, this is a very bad outcome, and we want to inform the system that this should not happen, but we don't know for sure when the incorrect decision was taken, because it could have been a turn taken a few seconds before, or choosing the wrong side of the road, or something like that. So we do not have immediate feedback for each decision, but sometimes we have feedback from an outcome that must be attributed to different decisions in the past. So this leads to some different problems, detailed problems that we need to solve to implement this kind of learner. And since this is not very used in bioinformatics, it's most used in things like games, robotics, things like that. But in bioinformatics, it has some very few applications. So we are not going to focus reinforcement learning, or even another kind of problem with semi-supervised learning and so on. So we're going to focus mostly on supervised and unsupervised learning. And now we're going to start with supervised learning. The basic idea is that we have a set of labeled data that we're going to use to train our model in order to find the best hypothesis. And we're going to assume that there is in the universe some hypothetical mapping, some function that allows us to map from the features, which is what we generally can observe, to some target that we want to predict. So these features can be, for example, the sequence of a protein and the target, the structure of a protein. The features can be the sequence of DNA and the target, a class, telling us whether or not this is a functional gene. The feature can be an array of gene expression data, and the class could be whether this is a tumor cell or a normal tissue cell, and so on. So there are many possibilities here, but the idea is that there is some way of mapping between the features that we can generally observe to the target value that we want to predict. And in our training set, we have everything. We have the features and the target value so that we can monitor the training of the model in order to check how many errors it's doing or what is its performance. So this would be supervised learning, and the goal is to find some approximation of this mapping between features and target values that will result from adjusting the parameters in our model. So we want to find this hypothesis that we can use to map between features and the target values. And it's supervised because since we have the target values in the training data, we can always check the performance of our different hypotheses when we are selecting the hypothesis. So for now, we're going to consider only the training set. We'll see that there are some additional problems here, but we're going to look at them later on. And the training set is the data we are going to use to adjust the parameters in our model. So basically, we're going to use to select the best hypothesis. The training error or empirical error is the error measured on the training set. This is also called sample error in some older literature, but nowadays it's generally called the training error. So this is when we measure the performance in the training set, we can measure it as the percentage of errors or how much far away from the target value we are when we are dealing with continuous predictions. And this is something that we want to minimize in order to find the best hypothesis. And the training error is simply measured on the training set. So for now, we're going to consider this problem of trying to predict the target values in our training set. The performance for this task, the measurement of performance in this task is the training error. We want to minimize that. And the data is the set of points where we both have the features and the target values. Now, there are two types of supervised learning problems here. Classification where the target values are discrete classes. And this basically makes us try to find a function that separates our data correctly into these different sets. And regression, in regression we are trying to predict a continuous value, and so we want to find a function that gives us predictions as close as possible to the target values that we have in the training set. So let's start with this one, because this one is very easy to visualize with simple plots. And we will look at polynomial fitting as an example of linear regression. The reason for doing this is to find here a technique, a trick, so to speak, that is very used in machine learning, which allows us to use some basic models in a much broader range of applications. So let's start with a single straight line, and this would be our model representing the set of hypotheses, which is the hypothesis class, which is the set of all straight lines. So the target value that we want to predict is some parameter theta1 multiplied by the feature value x, and then added with a constant parameter theta2. So we saw this previously, how to find the best line here. Suppose that this is the data that we have, the set of red points. We can draw many different lines in our hypothesis class, and we can find them by changing those two parameters. But the question is, how do we find the best line? We need some performance measure, and we saw that if we assume that the error is only affecting the y value, so y is some function that exists in a universe of x plus some random noise, then the expression that maximizes the likelihood of our parameters corresponds to minimizing this quadratic error, which is the sum of the squares of the difference between the target values and the values predicted by the hypothesis that we are choosing. So we can do this by gradient descent. We can compute the derivatives with respect to the different parameters and then slide down this error function until we find the set of parameters that minimizes the error. So this would be the best line, the best hypothesis so far, and we can see that this is not a very good model. We are considering only the hypothesis class of all straight lines, and since the points are not distributed along a straight line, we cannot find a very good hypothesis to fit these points here. So how can we fit something that is curved, this data set, by using just a linear model, so something that is straight, so to speak? One answer for this is changing the data. We can use a nonlinear transformation of the data and project it into a curved surface in a different dimensional space. Let's consider this operation here, where from our initial x value, we create a new training set that has the original coordinate here in x2, so the second feature is the original coordinate, but the first feature is the square of the original x. So now we have something that has two features, x1 and x2. We still have the same target values. We did not add anything new other than just the square of the original feature that we had. So now what we have is this problem in 3 dimensions, where we can use a linear model in 3 dimensions, which is a plane, to try to adjust our data. So looking at this graphically, we have the original coordinate here, which now we consider the second feature. We have the first feature, which is the square of the original values of x. And so the points now are the features of our examples are now here in 2 dimensions, because each example has 2 features, and they are spread out in the curve like this, because one of the features is always the square of the other feature. The target value is still the same, is the y that we're trying to predict. It has this goes up and then down and up again, this pattern. But now we are trying to predict this from 2 features in the input. So basically this plane here is the best hypothesis that we find by minimizing the quadratic error to try to predict the y values from the x values in the input. And if we consider only the line in this plane that is above the points that we have in our data, because these points are restricted by this relation, the second coordinate must always be the square of the first coordinate, then we have this curved line here, where which are the points in this plane on the best hypothesis that are above the points in our data set. So we can now project this back, and this is actually equivalent to this curve here, because what we did was actually fit the polynomial of degree 2 by taking these parameters for that plane in 3 dimensions, but using one feature as just the square of the other. We are actually fitting this polynomial here. And this is easy to do with gradient descent. You can use from numpy here polyfit. This function implements that. Given x, y, and the degree of the polynomial, it will use gradient descent to minimize the quadratic error between the predicted values of the polynomial and the target values, and it will give you the coefficients, so the values of those thetas that correspond to the minimum of the quadratic error. And now we can apply this to this data. So this is just the a line for loading the data from the file where we have these red points, x and y values for the red points. The x are on the first column and the y on the second column. So we are using here, the data structure here is a NumPy array with 2 dimensions, which makes it easy to extract the different columns. And now we can compute the coefficients using the polyfit function from NumPy and plot by first creating a set of 100 points uniformly distributed from 0 to the max value of x, so that we can draw this line smoothly when we compute the predictions for all of these x values. So this we can do by using the polyval function, where which receives as arguments the coefficients that we computed previously and this large number of values for x uniformly distributed here, so that we can then draw a line And remember that when we are plotting, the line segments are straight and are drawn between consecutive points. But since we have many points, we used 100 points, these line segments, even though they are straight, they appear to be a smoothly curved line. So this is just a trick for plotting this kind of graphs. We also plot the original data as red circles, and this way we can see the result here. Okay, so by increasing the degree of the polynomial on this argument, we can now do this for higher expansions. So this is the important idea here, is that if we use a nonlinear transformation to change the data, we can increase the power of our model in these higher dimensions. So we have new models that will now become more powerful if they are applied, for example, to data in more dimensions. And this way we can use something that, like a linear model, for example, to adjust our data in a way that is not linear in the original space of our data, because we're actually adjusting the linear model to a nonlinear transformation of our original data. And this is a general approach that is very used in machine learning and can help us improve the power of our models. So in this case, our inductive bias comes from the assumption that we can adjust the data with polynomials. That is, we are doing polynomial expansion on the x and adding x squared, x cubed, and so on. Then we do a linear regression in that space. But this basically just gives us polynomial curves in our original space. And this is our assumption, that we can use polynomial curves to fit the data. Because we are using these hypothesis classes, which are polynomials of some degree. But we can use different hypothesis classes as we increase the degree of the polynomials. So we could try to consider polynomials of degree 3, for example. We would get, this would be the best fit between the model and the data, degree 5, degree 15, and so on. And now here we can start seeing this effect, which is, even though a polynomial of degree 15 can adjust very well to the points that we have, much better than a polynomial of degree 3, it also starts giving us some strange predictions. So you can see here, for example, for an x value of 1, it gives almost minus 0.5, while the neighbors of this possible example are here over at 0.7 something. So this is very strange, this curve here, and it's probably wrong. It does not seem to follow the pattern of the points. So one thing that we can do, we can increase the power of our models as we increase these transformations, these nonlinear transformations, but we can also start deviating from what seems correct or what would work best because of what is called overfitting. The hypotheses that we choose are now so adjusted to the training data that even though the training error is small, the error outside the training data can be very large. And so we are losing the ability to generalize outside the training data. We are going to see this on a few lectures on how to solve this problem, but first we're going to take a look at classification 2. So for this lecture, we saw the basic idea of machine learning. We are trying to solve problems for which we do not have the algorithm. We don't know what is the algorithm to solve them, but we use a more generic machine learning algorithm that will explore a set of hypotheses, this hypothesis class, and pick the best one that will give us the solution to our problem. So it will give us an algorithm that solves our problem. Of course, this will not be an algorithm that is easy for us to understand, because it can be just a set of operations. For example, this, if we compute the actual values for all of these parameters, this gives us an algorithm. We can just multiply x raised to the power of 15 by one specific value, and then raised to the power of 14 by another, and so on, and obtain the prediction for y. So it gives us an algorithm, but it's just a series of elementary operations to obtain the result. And this is especially useful if we do not know what the algorithm should be. So if we do not know what is the relation between x and y, we can try to find it on the data and adjust some model to obtain that result. In supervised learning, we have labels in our data. We are starting to see this kind of problem. We saw regression, which is when we try to predict some continuous value. We're going to see classification in the next lecture, which is when we try to predict some discrete class labels. We saw in this particular case solving the problem of linear regression by maximum likelihood, which, under the assumption that the error is on the target value, results in minimizing the quadratic error, so least mean squares optimization. And we saw this general idea that we can increase the power of some linear models by transforming the data non-linearly first, and this gives us the ability to, for example, expand the data into higher dimensions in a way that allows us to solve the problem better by using linear models in higher dimensions. This is a general trick in machine learning, because we can always transform the data in some way to make the problem easier. Instead of using more or different kinds of models, we can just solve the problem by transforming the data. But also we have this problem of overfitting, which is we may find that the hypothesis is so strongly fit to the data that we are losing the ability to generalize from outside the data. But we'll see this how to solve this problem later on.